Right, we're going to start quite quickly on this one because we want to catch up a little time from the first one. So our next talk is what is the hype around hyperspectral, and we've got Isabel Crozier Morris to do that. So over to you.
Sure. Hello everyone, thank you for joining me for the talk. I'm inspired by the last speaker to do a tiny bit about me first, because I didn't actually put that on the slide. So I am a geographer from the start, did a geography degree, and then worked for Ordnance Survey for 5 years. So this is actually my first FOSS4G, which is quite exciting. And I'm now moved over into Earth observation kind of permanently as such. So I was in the research team at Ordnance Survey previously as a research scientist specialising in Earth observation, and then a few months ago made the jump over to the Satellite Applications Catapult. So just briefly, who actually has heard of the Satellite Applications Catapult here before? Put hands up. Okay, that makes my life slightly easier. So very briefly, the Satellite Applications Catapult is funded by Innovate UK and recently moved to a new strategy based on 3 missions. So we've got the 3 missions up here on the screen. I'm based in the Sustainable Earth missions. That's kind of the centre point that we'll be focusing on. But the Catapult and with my colleagues do lots of work with like drone testing, also things like edge computing for satellites and kind of lots of different parts of technology. So happy to talk all things remote sensing. Just to note as well that the Catapult is spread across the whole country in the sense that we have this UK space ecosystem where there's lots of different clusters that we support. So there's lots of different kind of pieces of work happening. I'm based in the head office in Harwell in Oxford. So to begin, I appreciate some of you may know this, but I thought it'd be good to set the kind of base point and then we'll work our way up to actually understanding hyperspectral and its applications. So what is Earth observation? Got the definition up here. The kind of key thing to take away from this is that there's many different applications of Earth observation. People mean different things when they say it. So you've got obviously the satellites, you've got drones, you've got many different kind of ways of having this remotely sensed information. The kind of key thing on here is the fact that you've got these applications, but there's so many ways of implementing it and combining it with other data sets. And that's when you move from that kind of initial information that you can get from, say, the raw data from the satellite imagery onto insights and then actually making an impact. So I've kind of got some of the geospatial data sets on the right-hand side there. It's when you actually go and combine all of these, that's when we can deliver the most impact for the real world. So I'm going to start off with a few defining kind of characteristics of Earth observation. So we're going to work through these 3, starting off with spatial resolution. So I have an image here. So this is Sentinel-2, which is a European Space Agency open source satellite image. So some of you may know this is an example of a multispectral image. So when we kind of talk about images, and a lot of you would have used Ordnance Survey data here, so that a lot of that data comes from originally from their planes when they're flying Great Britain and capturing information. So that's 4-band imagery that Ordnance Survey would use: red, green, blue, near infrared. You then move up to multispectral when you're in the region of kind of 8 to 13 bands of information. So with Sentinel-2, you've got 13 bands, and this is an image basically over where we are here. It's a 10-meter spatial resolution. Spatial resolution is important because depending on the object or what you're looking to analyze, you would potentially have a mixed pixel if you don't get down to the granular enough information for what you're looking at. So if you're looking at a level of a field or something like that, 10-meter resolution would be perfect. If you're then looking at something which is much more detailed, like an individual tree, you'd then be wanting to kind of get down to more few meters or say 50 centimeter spatial resolution to be able to actually analyze that individual tree. Then spectral characteristics. So kind of got a few different bits on the slide here. So with satellite imagery, you tend to group it into 2 buckets: optical satellites and radar. So optical satellites are the kind of the true color, false color, mainly on the left-hand side. So with those ones, it can almost like just having a camera, but on a satellite whizzing around the Earth, and you're able to capture lots of bits of information. We've got the visible light spectrum, which is in the middle. So that's where the kind of true color comes in, and then the false color comes in when you move towards the edge of that, when you've got, say, near infrared information. You also have thermal satellite imagery. So this is still an optical example, but you can get additional kind of bits of analysis from that. And then you've got radar data, which is kind of an entirely different beast in the sense of anyone here who's tried to pre-process radar data. It's a lot more challenging than, say, optical, many different stages, but it's completely different type of information you can get from that. So you can get small changes in elevation, for example, using interferometric synthetic aperture radar data, or INSAR, which is a much nicer way of putting it. And then you've got cadence, so how often you can get the data. This was a lovely GIF, but when I put it into the PDF, couldn't get the lovely GIF to move. So we now have a still of the GIF. But basically what this is showing is a snapshot. It is 2017, it's a bit outdated, but it shows lots of different satellites and their overpasses of one day. And you've then got the kind of boxes is each swath that it takes. So you've kind of got the swath coming down, and then you've got individual kind of subsets of that. And what this is showing is that there's lots of different types of satellites. They've got different spatial resolution. So on the Legend, you've got, say, like 1,000 meters for the first one, all the way down to 10 meters for the Sentinel-2 that I was just talking about. So there's different kind of options there. But the main thing is, the more often you're able to get the imagery, the different applications you can use it for. So that's one of the challenges with, say, like remotely sensed data. When you've got aerial imagery, if you're capturing it every couple of years, there's lots of change that will happen in between that. So how can you actually capture that as well? Wanted to just put this up just briefly, just to show lots of different applications of satellite imagery. So I'm going to be moving on to hyperspectral in a minute, but there's so many different things that you can touch upon. And I'm happy to talk about any of these kind of afterwards in the coffee breaks. So, hyperspectral imagery. We've mentioned the 4-band aerial imagery, then multispectral. So what is hyperspectral? So what we've got up on here is the electromagnetic spectrum again. And the main thing to take away from this is, with hyperspectral imagery, it's characterized by having lots and lots of bands. So normally you'd have hundreds of bands for hyperspectral. But the reality is, what actually makes it hyperspectral is the very small gaps in between the bands. So from that, you can get a near continuous spectrum, and then you're able to do lots of additional analysis with that extra information. So with hyperspectral imagery, so we had previously just kind of the visible spectrum and then like the near infrared. You could tend to be able to get into the short wave and then sometimes the long wave infrared as well. And from that, there's extra kind of bits of change that you're able to look at to distinguish between two things which are very similar. So what we've got on here is 2 examples. I mentioned Sentinel-2 already. So this is the multispectral satellite. And then we have Prisma. So these are both open source examples, being FOSS4G. I'm trying to stick to more of the open source side of things. Prisma is a satellite from the Italian Space Agency. And what you can see for the same wavelength, basically. So with Prisma, it extends further, but for comparison, we've just kind of cropped it using this image here. And you can see there are many more bands for the same spectral wavelength. But you can also see there's a little line in between each one. So there is still a gap between the two. I think with Prisma, it's something like 10 nanometers. But compared to the gaps that you've got between the Sentinel-2 bands, you're able to get into a lot more detail. Also wanted to mention hyperspectral data cubes. So that's what's in the top right-hand corner. So it's basically an attempt of a visualization to be able to say, when you've got 1 pixel, you're looking, if you kind of say load it into QGIS or something, you're looking at something that makes sense to the human eye and is normally kind of visualized as an RGB. But the reality is there's so much more information underneath that. So that's kind of just highlighting the fact you've got loads and loads of stacks of bands that you're then just picking out 1 or 2 to actually visualize it. So I kind of mentioned this before. So when we're talking about hyperspectral, you're able to get a lot more information and get what you can call a spectral fingerprint. So that's what the fingerprint at the bottom right is referring to. The more bands that you have and the kind of more continuous the spectrum is, the more detail you're able to get, and the easier it is to distinguish between 2 things which are very similar. So if you think like an orange and a pumpkin, they're both orange, but they are slightly different in color. But depending on the spectral resolution that you have, so kind of how continuous the spectrum is, it might be difficult to actually distinguish between the 2. The same concept goes for 2 things that, say you might have a healthy tree or an unhealthy tree. Having this detail means you're able to distinguish between the 2. So we have spectral fingerprints, and then we have what's called a spectral signature. So each material or object will have its own spectral signature. And then you also will have, say, the healthy or unhealthy versions. If they've got affected by a particular disease or something, that will also have its own spectral signature. So what we have on the top right-hand corner is just an example image where you had these different like agricultural fields, and this is an example of a healthy crop, so to speak. And in the bottom left-hand corner, we've just got a few examples of different spectral signatures. So the point with this is the fact that if you've only got a few bands, it's difficult to be able to get as much information as when you've got this continuous spectrum. I'm going to touch on a couple applications of hyperspectral imagery. There are many, many more, which I'll be more than happy to talk about after this, but kind of in given the time. So this is water quality, and there's been some really interesting studies using the Prisma and Sentinel-2 comparison that I was talking about before. So what you've got on the right-hand side is some kind of different analysis, but the main takeaway was, I should note that the Prisma satellite has a spatial resolution of 30 meters compared to Sentinel-2 of 10 meters. So it's, with hyperspectral imagery, it's something that is kind of increasing a lot, and I'll touch on this in a minute, but you can still get more value, depending on the use case, out of a 30-meter hyperspectral pixel compared to a 10-meter multispectral pixel. There are sort of lots of launches and things coming up which are bringing the spatial resolution way down, although that's more on the commercial side of things, but I'll touch on that in a minute. Well, actually, I'll touch on that now, given on the left-hand side, we've got Pixel imagery. So Pixel is one of the example companies that are launching lots of commercial satellites for hyperspectral. So Pixel's latest launches are bringing the spatial resolution down to 5 meters. So when I'm saying sort of what's the hype about hyperspectral, there's so many advances that are happening at the moment. Hyperspectral technology has been around for a long time, being used with like imaging spectrometers and used by a lot of the catering sector actually to look at whether things are going moldy. So I was very confused when I first did my kind of like research into hyperspectral and was going, why are all these things of cakes coming up from all of the scientific literature? Then had to add on some extra keywords and then made it to things which were a bit more relevant to what I was looking for. But it's the technology itself isn't new, but the way it's being applied, I guess the scalability is starting to really step forward. So another application, and this is something that people don't tend to think of as hyperspectral, but is hyperspectral. When you're looking at particular pollutants, so if you're looking to detect greenhouse gases, when you have hyperspectral imagery, you're able to narrow in on, when I'm talking about different materials, if they're healthy or unhealthy, you can also look at the kind of atmospheric column and then pick out individual pollutants. So in this case, this is a methane map. With this technology, you've got freely available satellite, it's called Sentinel-5P by the European Space Agency, but the spatial resolution's on the kilometre scale. So that's really useful for regional analysis, but what's happened in the last few years is companies such as GHGSat have really stepped up the spatial resolution capabilities. So GHGSat, their satellites have spatial resolution of 30 meters, and you're able to get down to methane releases of 100 kilograms. So that's a much smaller emission. It's still a large one, but compared to something like Sentinel-5P, you're able to get that granularity. So this is an example of a pollution event in the UK. So this was where there was some waterworks happening, and unfortunately they hit a gas like mains while they were doing their work. Local residents smelt the gas. Happened to be nearby someone who was a PhD student who was actually studying some of this work, so they knew someone at GHGSat, and they got the satellite tasked to come over and capture some data, and then this was kind of the output of that. So gas leak detected. One thing I should say as well with satellite imagery, there's some satellites which are constantly orbiting and always capturing information, capturing images, and there's other satellites which are basically, they still follow an orbit, but they need to be turned on or tasked by someone to actually capture an image. So something like GHGSat, they've got a constellation of satellites. So they've got something like 10, I think, which are up there at the moment, but they're not necessarily always capturing information. So sometimes you've got people will combine, like in this case with the methane, the Sentinel-5P open source imagery, and then they'll be able to detect that something's happening here, and then the GHGSat satellite or others will then get tasked to go to the site and then capture more granular information. I wanted to touch a little bit on actually accessing hyperspectral imagery. So I've kind of got the screenshot here. Apologies, it's quite blurry. This is from QGIS. So this is a plugin that's available called Nmap. So Nmap is another hyperspectral satellite from the German Space Agency, and they've done a lot of work into this QGIS plugin. So it's most kind of tuned in for Nmap, but you can still use it for other hyperspectral imagery. There are quite a few challenges with hyperspectral imagery in the sense that when you tend to have so many bands that come with it, it's a lot of kind of data, it's a lot of storage required, and kind of additional processing as well that comes with it. So what people tend to do is there's a kind of a mixture of ways of dealing with this, but being able to do some initial analysis and something like QGIS is quite suitable. But if you're going into more, depending on the level of detail, basically, of the analysis you want to do, there's commercial software out there like Envy, which is specifically tailored to the latest academic algorithms for hyperspectral data. But if you want to have a look, have a play around, do some initial analysis, then you're able to do this in QGIS, which I think is very cool. I mentioned Prisma and Nmap, then Wyvern as well. So this is a commercial satellite company. There are another one like Pixel, which are recently launching a real step up in the spatial resolution of hyperspectral imagery. And they have a scheme at the moment where you're able to access some of their latest launches, like not for commercial use, but for research, or if you just want to have a look at it. So I included that link there as well. And yeah, basically there's just so much out there of hyperspectral at the moment. It's a real step change. It's a great time to be kind of getting up to speed with what hyperspectral imagery is, what it can be used for, and being able to kind of understand it, because there are some additional challenges, as I mentioned, with the extra data load and that side of things. But there's so much that you can do with it. So it's a very exciting time for hyperspectral. So thank you very much for your attention. I have recently written a blog, which I've included the link at the bottom. So the slides are in my kind of talk. So I mentioned some of the challenges I was just talking about. There's a little bit more information in that in my blog, but given the time, I didn't kind of dive into that. But thank you very much for listening. Looking forward to any questions.
Okay, any questions? Yes, Paul.
Yeah, great. Thanks for that talk. Really interesting. I was just wondering, obviously, one of the challenges with multispectral imagery is cloud color shadow. With hyperspectral, what's the kind of how far developed the masking algorithm how far advanced are they?
So that question was, how far advanced are cloud masking algorithms for hyperspectral imagery? So it's something so hyperspectral is still affected by clouds in the same way that multispectral is. The algorithms are starting to be kind of more developed. Something like the Prisma satellite that's been around for 5 or so years, there's much more work's been done into that. I guess in the same way with Sentinel-2, how much research has kind of ramped up with the cloud masking side of things. So yeah, those type of algorithms are getting there. I think with the 5 meter spatial resolution imagery, which has either like literally just been launched or within the last year, that's kind of lagging behind a little bit. But I think that will be kind of improving in the next 6 months to a year.
Yeah, I'm really interested in the fingerprinting bit. Do you add a time element to that as well? For example, an oak tree looks different in the winter than the summer.
So that was about spectral fingerprints changing of seasons. So yes, yeah, there are different spectral signatures depending on the time of season. So yeah, if like an oak tree, it will have a specific brown color, and then in the summer, well, when it gets its leaves, then yeah, it will have a different signature as well. So one thing to mention is the US Geological Survey have like literally thousands of spectral signatures that you're able to go and download, and you'll get one of those little kind of spectral signature graphs. You can then import them into different pieces of software. So for example, Envy that I mentioned, you can import that spectral signature and then do a kind of, does this pixel match yes or no type classification. So yes is the answer.
So I've seen a lot of like work around segmenting and extracting features just from like satellite imagery. So like you've got like image of some urban area and you're extracting the houses or so forth. This sounds really interesting because this, like, kind of going back to the fingerprinting thing, it seems like it would be much easier to be able to start segmenting and extracting features when you have multiple layers of information to kind of
interpret what that kind of object is.
Mhm.
I'm assuming there must be lots of people like researching this, or I haven't heard much about it, but it just feels like it would be so good for feature extraction from that.
So the question was around thoughts on feature extraction with hyperspectral imagery. So yes, yeah, that's something that is being looked at and is a real capability for hyperspectral. Not just in terms of, I guess, feature extraction of like buildings, but also if you want to do something like roof material analysis, then you're able to do that level of information. I'd say there's because of the extra challenges with the amount of data that you've got and things like that. I think it's something that's being looked into as how you can kind of integrate hyperspectral imagery better into something like I guess the more complex deep learning kind of side of things when you talk about segmentation. The sort of shallow machine learning I think is challenging, I think, with hyperspectral, just given the some of it needs to be a bit more fine-tuned given the extra characteristics. But yeah, there's real potential there. People are already using it, especially for things like minerals in the ground, like that side of things, like pollution, contaminated land. That's already being used a lot, given some of the limitations of the spatial resolution side of things with the open source. But now we've got these kind of improvements coming in, and there'll be even more, I think, for say buildings or other objects.
Hi, firstly, thanks for the great presentation. It's like a super clear explanation. I had a question. I think, if I understand it correctly, correct me if I'm wrong. I mean, GHGSat is focusing very, very specifically on sort of spectral signature, pixels for work, and it's hyperspectral, but capturing lots and lots of the spectrum. But are there any other suppliers doing stuff like GHGSat but for another use case, or a sort of specific use case, just sticking a constellation up for that particular scenario?
So that was a question around GHGSat specifically for methane, but then other alternatives for which companies are looking at specific spectral signatures. So there's carbon dioxide is another gas that there's been particular companies looking at. I mean, funny enough, GHGSat have also launched a satellite looking at carbon, but there are a couple other ones as well. I think it's Carbon Mapper was one of the most recent ones looking at carbon dioxide, but it seems to be specifically with greenhouse gas pollutants where they're focusing in on one particular thing at the moment, and then other satellite companies, someone like Pixel, they have particular bands that they're focusing on. So even though they're going for it's hyperspectral imagery, they're focusing on a specific range, and then there's particular use cases for that. So say like they've got mining companies lined up, or water companies for water quality. They're not necessarily doing the full range of, when I was saying, say from 400 nanometers to 2,500, something like that. They're picking, 400 to 1,000, but the bands they're supplying are for particular use cases. So in a way, they're focusing on certain bits, but not, I guess, quite to the extreme level of, say, methane or carbon dioxide.
Another question over the back.
Yes.
More of a comment, actually, just to extend on that. I've seen work done with helium and gases as well, allegedly from sensible 2 data. Not sure how robust it is, but it's something to be.
Oh, that's interesting. Thank you. I wasn't aware of that.
Yeah.
So there are like hundreds of plans looking at satellite
Is that dimensionality reduction? You said I missed one word halfway. Yeah, the question was around basically dimensionality reduction for hyperspectral. So yeah, there are different methods out there. So dimensionality reduction is a key thing that needs to be done to hyperspectral to then be able to extract the information you need. There's different types. There's minimum noise fraction is one, and then principal component analysis being another. They're two kind of the most common ones for hyperspectral. It depends whether when you're doing a spectral signature analysis, you want as much of that information as possible. But there's other types of analysis you can do for hyperspectral where you'd rather remove a lot of the noise and kind of reduce that data down in a different way compared to when you want to keep all the bands of information, but you kind of want to reduce it in that way. So So yes, there's a lot of work that's been done with that. There's more on that on my blog. It's kind of cheeky way given the time. So happy to discuss more.
Yeah. We'll probably just about manage one more question if anyone's got one. Yeah.
Where are things heading with resolution? So 5 meters,
Mhm.
from my perspective, that number seems to be down.
Mm.
What's the kind of path of travel? When does it start to get into kind of flying a plane resolution?
So from the satellite perspective, that's quite far off. So a lot of the satellites that, even commercial ones that are being launched at the moment, Planet just launched one called Tanager. That's still a 30-meter spatial resolution. Hyperspectral increasing that spatial is really challenging. So I think that's probably, I don't know, 5-10 years off at the moment, given the 5 meters literally coming out now, like in the last 6 months and in the next few years. I think quite a lot of the improvements with the latest launches has been the spectral resolution, so that gap in between the bands coming down from say 15 nanometers more to 10 or 5. So there's kind of different buckets of increases of resolution that are happening. So not just spatial but spectral. So yeah, I'd say down to the like aerial equivalent is a long way off, but there are a lot of hyperspectral cameras which are just put onto aerial platforms and then also drone platforms. So I guess you can get that spatial resolution, but just not from satellites at the moment.
Is it similar for the radar?
As in what? As in just in general?
Yeah.
So I mean, radar you can get down to 30 centimeters now, with a kind of very tiny little area that you're looking at. So it's been quicker to advance the technology in that sense. I think hyperspectral people aren't aware of it as much. It's kind of lagging behind, I guess, in terms of the market for it. So I think that might be partly why. But yeah, the radar data is already you can get equivalent to aerial platforms now from the commercial satellite providers. The open source tends to be 10 meters spatial resolution, like Sentinel-1 from European Space Agency.
Okay, thank you very much.